Swayam Prabha. Digital India. Educated India.
Welcome to the fourth week of this open course on diffusion in multi-component solids. This is the 15th lecture in this series, and in this lecture I will discuss how diffusion in multi-component system can be described based on Onsager's formalism of Fick's law. We will also see how Gibbs-Duhem equation along with use of an appropriate frame of reference helps to reduce the number of interdiffusion coefficients from n square to n minus 1 square in an n component system. So we have seen the expression for Fick's law for diffusion of a component J equal to minus d dc by dx. Now in this expression d is constant, which is called diffusivity, and remember it is valid when the concentration gradient is very small, because only then d is constant, because we have derived this expression for d equal to 1/6 gamma alpha square, where gamma is the successful jump frequency and alpha is the jump distance. If the composition changes, both gamma and alpha would change, right. So d is a function of composition. So only when we have a dilute solution or small concentration gradient, you have d constant and you can use this expression. But if the concentration gradient is larger, then we know that d has to vary with composition, because in the concentration gradient C varies as a function of x. So obviously d will also vary with x. In fact, under the concentration gradient, or if the concentration gradient is larger and if there are interactions between the atoms, the thermodynamic interactions are stronger, then in fact the jump in forward direction is not same as in the backward direction. So we need to take that into account, and the expressions for diffusivity will become more complicated. Okay. So d is a function of composition, but it does not depend upon the gradient of composition. Just like in Fourier's law, thermal conductivity does not depend upon the temperature gradient, and in Ohm's law electrical conductivity does not depend upon gradient of electric potential, right. Similarly, diffusivity does not depend upon gradient of concentration, but it does depend upon composition. Okay. So that, keep that in mind. In fact, whenever there is a diffusion occurring at any given plane or at any given x, the composition also varies with t, right. So we should more appropriately write this as minus d dou c by dou x, partial of c with respect to x. This sign for partial we will call it dou, because c is a function of x and t. So how we take into account parameter t, we will talk in the next class, but right now keep this in mind. Okay. In fact, this is valid only for binary systems, diffusion of component one into the other. If we have multi-component system, then we need to modify this expression, right. So let us look at Fick's law as applied to multi-component diffusion. A multi-component system means it has typically 3 or more components. So if we consider n component systems, let us say component 1, 2, 3 dash 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 n, then we use Onsager's formalism and extend the Fick's law using Onsager's formalism. So, using Onsager's formalism we express the flux as a linear combination of all the concentration gradient the flux of a component I for example. So, if we write the flux of component say 1, it is denote this by J1 tilde. So, tilde denotes that we are considering interdiffusion, right, or diffusion due to the strong concentration gradients. So, J1 tilde as a linear combination of all concentration gradients. Since we have n components, there are n concentration variables and n concentration gradients, right. So, we need to express this as linear concentration gradients, linear combination of n concentration gradients. So, which we write as dou C j by dou x, where j is equal to 1 to n, and the corresponding coefficients we denote as d, the effect of 1 onto flux of 1 we denote as d11 tilde, and obviously we give negative sign. Similarly, d12 tilde and so on. For component n it is d1n tilde. Similarly, the flux of 2 we express as d21 tilde dou C1 by dou x minus d22 tilde dou C2 by dou x d2n tilde dou Cn by dou x, and we have n such flux equations. So, J n tilde would be minus d n1 tilde dou C1 by dou x minus d n2 tilde dou C2 by dou x till n tilde dou Cn by dou x. So, how many coefficients we have? For each flux we have 1, 2, 3 n terms, and there are n such fluxes. So, n times n, the total n square these are called interdiffusion coefficients. Okay. But all of them are not independent. Why? Because there are constraints on both the concentration gradients and the fluxes, which means not all concentration gradients are independent. Similarly, not all fluxes are independent, provided we use the right frame of reference, right. I have introduced you to the different frames of reference that we use. So, it is worth to mention here that most of the time the volume fixed reference frame is used for diffusion measurements. Okay. So, that is most popularly used frame of reference. So, in specifically volume fixed frame if we consider, then all n fluxes are not again independent. So, we can reduce some of these coefficients. So, let us see how do we reduce the number of coefficients using the constraints on gradients and fluxes. So, first consider the constraint on concentration gradients, and its origin lies in the Gibbs-Duhem equation, right. We have seen the Gibbs-Duhem equation during the refreshers on thermodynamics, right. So, if we apply Gibbs-Duhem equation to partial molar volumes, what do I get? x1 dV1 bar plus x2 dV2 bar xn dVn bar equal to 0. So, if we multiply both sides by Vm, which is the molar volume, if we divide by Vm, which is the molar volume. So, V1 bar, V2 bar here are the partial molar volumes of components 1, 2 up to component n, and x1, x2 denote the mole fractions of components 1, 2. So, we can write x1 by Vm dV1 bar plus x2 by Vm dV2 bar now what is xi over Vm? Is what? Ci, right, where Ci is the concentration in number of moles per volume unit, meter cube or centimeter cube, right. So, we can write C1 dV1 bar plus C2 dV2 bar plus Cn dVn bar equal to 0, which means sigma Ci dVi bar equal to 0. But we know what is Ci Vi bar? Is the Ci Vi bar is the volume fraction, right. Remember we have derived this some time back. So, Ci Vi bar is phi I, which is nothing but the volume fraction of I, and so sigma Ci Vi bar should be 1, the summation of all volume fractions should be equal to 1. So, if we take the differential, sigma Ci dVi bar plus sigma Vi bar dCi should be equal to 0, and this we know from here is already 0. So, we have sigma Vi bar dCi equal to 0. So, if we differentiate with respect to x coordinate, we can write more specifically for this as V1 bar dou C1 by dou x plus V2 bar dou C2 by dou x so on to Vn bar dou Cn by dou x equal to 0. So, this is the constraint that we have to use. So, we can write the constraint, we can write here as dou Cn by dou x is equal to negative of V1 bar over Vn bar x plus V2 bar over Vn bar up to n minus 1 component Vn minus 1 bar over Vn bar dou Cn minus 1 by dou x. So, if we substitute for dou Cn by dou x, so suppose if we substitute for J1 tilde, if we substitute in the equation for J1 tilde, substitute for dou Cn by dou x, we replace this term by this term on the right hand side. So, this negative becomes positive and we have d tilde 1 n times V 1 bar over V n bar times dou C 1 by dx and so on. So, we will get, and then we rearrange to take out the gradient terms individually, then we get minus d 1 1 tilde minus d 1 n tilde V 1 bar over V n bar dou C 1 by dou x minus d 1 2 tilde is d 1 n tilde into V 2 bar over V n bar dou C 2 by dou x minus so on till the n minus 1th term d 1 n minus 1 tilde d 1 n tilde into V n minus 1 bar over V n bar dou C n minus 1 by dou x. So, each of this term we can substitute with one term. So, this one we can substitute with one term which we denote as d 1 1 tilde superscript 3 superscript n sorry. So, each of these term we denote as d 1 1 tilde superscript n in this particular case. Similarly, this one will be d 1 2 tilde n so on till d 1 n minus 1 tilde n dou C n minus 1 by dou x. So, in general we can write dou I j tilde n is equal to d I j tilde minus d I n tilde times V j bar over V n bar, which means not all of these n coefficients are independent, but we have only n minus 1 independent coefficients for a given flux term. Now, how many such fluxes are there? There is also a constraint on fluxes, and what is that constraint? So, constraint on interdiffusion fluxes, and if we use volume fixed frame, the constraint is sigma G I tilde V I bar should be equal to 0. Remember, our fluxes here are expressed in the unit of moles per centimeter square or meter square per second. So, we can write J 1 tilde V 1 bar plus J 2 tilde V 2 bar and so on plus J n tilde V n bar should be equal to 0, which means J n tilde is given as minus V 1 bar over V n bar J 1 tilde plus V 2 bar over V n bar J 2 tilde and so on V n minus 1 bar over V n bar J n minus 1 tilde. So, again not all n fluxes are independent. So, nth one is dependent, only n minus 1 independent fluxes. So, we have each flux expressed by n minus 1 independent terms, and there are n minus 1 such independent fluxes. So, total n minus 1 square interdiffusion coefficients. So, in general we can express, if we write equations for all n minus 1 fluxes here, then we express the flux of any components J I tilde equal to minus summation of d I j tilde n dou C j by dou x. J here varies from 1 to n minus 1, and also I is from 1 to n minus 1, and so there are n minus 1 square interdiffusion coefficients. Clear? So, this is how we can express interdiffusion in a n component system. We can describe interdiffusion in n component system by using Fick's law extended to the multi component system by Onsager's formalism. So, we need n minus 1 square interdiffusion coefficient to completely describe interdiffusion in an n component system. Moreover, the set of these n minus 1 square interdiffusion coefficients are functions of composition, which means with varying composition this set will vary, or for a given composition we have a fixed set of n minus 1 square interdiffusion coefficients. If I describe this for a ternary system in order to understand this. So, consider a ternary system of copper, nickel, zinc. So, which component to treat as dependent component is our choice. We can treat either copper or nickel or zinc. So, if I treat zinc as dependent, then I have two independent fluxes, one for copper, one for nickel. So, I can write J tilde copper as minus D tilde copper copper superscript zinc. The superscript refers to the dependent component, times the gradient of copper minus D tilde copper nickel zinc gradient of nickel, and J nickel tilde should be minus D nickel copper zinc superscript dC copper by dou x minus D nickel nickel tilde zinc dou C nickel by dou x. So, I have 4 interdiffusion coefficients in a ternary system, right. So, n minus 1 square, 3 minus 1 is 2, 2 square is 4, because there are 2 independent fluxes and 2 independent concentration gradients. So, in this case D copper copper, D nickel nickel, or D I j tilde n, where I equal to j, in this case they are D copper copper zinc and D nickel nickel zinc. These are called main interdiffusion coefficients, right. So, D I tilde n's are called main interdiffusion coefficients, and they quantify the effect of concentration gradient of I on its own interdiffusion flux, right. So, it is basically the contribution of concentration gradient of I on its own interdiffusion flux. Dij tilde n, where I not equal to j, are referred to as cross or interactive interdiffusion coefficients. So, in this case d copper nickel and d nickel copper are the two cross interdiffusion coefficients, and they are basically the contribution of concentration gradient of J on the flux of I. So, these are basically the quantification of what we refer to as diffusional interactions. Or the cross effects. So, these cross coefficients quantify the cross effects, meaning if we consider d copper nickel zinc term, when we use zinc as dependent, it means how the gradient of nickel is affecting the flux of copper. Similarly, d nickel copper indicates how the gradient of copper is affecting the flux of nickel. So, d copper nickel quantify the interaction of nickel with copper, and d nickel copper quantifies the interaction of copper with nickel during the diffusion. Clear? So, now when we write the cross terms and the main terms, right. For example, in a ternary system, if I write J1 tilde equal to minus D11 tilde 3 dou C1 by dou x, D12 tilde 3 dou C2 by dou x. The main term most of the time it will be positive, although it is not necessary, because D11 tilde 3 is D11 tilde minus D13 tilde, but D13 the cross effect 13 would be much smaller compared to the main term D11. So, most of the time this term will be positive. The cross term D12 tilde 3 may be negative or positive. What does it mean? Basically, if D12 tilde is negative or positive. If D12 tilde is positive, which means the interdiffusion flux of 1 is enhanced down the gradient of 2 and reduced up the gradient of 2. Similarly, if D12 tilde is negative, it means the interdiffusion flux of 1 is enhanced up the gradient of 2 and reduced down the gradient of 2. So, let us try to illustrate this. So, let us call this as term 1, which is the main term. Remember, we need to take into account both gradient and coefficient, right. So, let us call this as term 1, this is term 2, including this negative sign. So, let us suppose this is always positive, then the first term should be depending upon the sign of the gradient. Remember, it again the entire term may be positive or negative. So, what is the convention? Typically, the flux, if it moves from left to right, it is given a positive sign. If the flux is from right to left, it is given a negative sign. So, let us consider two cases. So, I am allowing the diffusion between two different compositions of alloy 1 to 3. So, let us say first one is 70 30 0 and second terminal alloy is 100% of 3, right. So, if I write this as 1, this as 2 and this as 3, 2 and 1. The second case, so in this case component 1 component 2 are moving in the same direction. In other words, both the gradients have same sign. In this case, what is the sign of gradient of 1 and 2? Negative gradients. Okay. So both dou C1 by dou x is less than 0 and dou C2 by dou x is less than 0. The second case I am considering when the two gradients are opposite. So let me assemble 70, 0, 30 with 0, 100, 0. So the second alloy contains 100%, second terminal where was 100% of component 2 to start with, and this is again 70 and 30. This is my component 1, this is component 3. So in this case now the two gradients are opposite. So dou C1 by dou x is negative, but dou C2 by dou x is positive. Yet as I am increasing x, the concentration of 2 is increasing, that is why the gradient is positive. So if D12 tilde 3 is greater than 0, what does it mean? If D12 tilde is greater than 0, first term is positive, we know, because this gradient is negative, so the term is positive. If D12 is also positive and this term is negative, so this term will be positive. So both the terms are positive, which means the flux of 1 is enhanced by enhanced down the gradient of 2, right, because D12 is positive. If it was negative, what should happen? Term 1 is positive, but D12 is negative, so this overall term becomes negative, because negative negative is positive and there is one more negative term here. So the first term is positive, second term is negative. So the cross term is having a subtractive effect, that is why we say the flux of 1 is reduced. So here term 1 is greater than 0, but term 2 is less than 0, right. So this is an additive effect when D12 is positive, and when D12 is negative, subtractive effect. So we say that the diffusion of 1 is reduced down the gradient of 2 if D12 is negative. Now in this case we will have the reverse scenario, right. If D12 tilde is greater than 0, then obviously this is positive and this is positive here, the gradient also positive. So this term is negative, and so we will have subtractive effect. So we say if D12 tilde is positive, the flux of component 1 is reduced up the gradient of 2, and if D12 tilde is less than 0, we will similarly have additive effect. Clear? So now here we have expressed the fluxes of copper and nickel with zinc as dependent component. Now I can very well write these equations with copper as dependent component, right. So if we write, let us say copper as dependent component, then I will get equations for two independent fluxes will be zinc and nickel. So, I can write D zinc tilde copper dou C zinc by dou x minus D zinc nickel tilde with copper dou C nickel by dou x, and the nickel flux will be D nickel zinc tilde with copper as dependent minus D nickel nickel tilde D C nickel by dou x. So, I get a different set of interdiffusion coefficients. Now, these two sets are different, like D nickel nickel with zinc as dependent is not the same as D nickel nickel, sorry, this should be copper. Okay. So, D nickel nickel with copper as dependent is not same as D nickel nickel with zinc as dependent, okay, but they are interconvertible, that you can show. You can also have the equations with which we can convert from one dependent component to the set with another dependent component for an n component system, that you do as exercise. Basically, there are only 4 independent coefficients for ternary. We do not say 4 plus 4 8, because this once you have this set you can obtain the next set. So, you can use them depending upon whichever component you want to use as dependent component. Okay. Now, let us try to apply Onsager's formalism of Fick's law to binary system. Binary means 2 components, right. So, we have only one independent interdiffusion flux, one independent concentration gradient. So, if we treat 2 as dependent, then we can write J1 tilde equal to minus D11 tilde 2 dou C1 by dou x, and if we treat 1 as dependent, then we can write flux 2 is independent, we can write it as J2 tilde is equal to minus D22 tilde 1 dou C2 by dou x. In the original Onsager's formalism, we will write D J1 tilde is equal to minus D11 tilde dou C1 by dou x minus D12 tilde dou C2 by dou x, and J2 tilde equal to minus D21 tilde dou C1 by dou x minus D22 tilde dou C2 by dou x. And if we substitute for dou C2 by dou x here or for dou C1 by dou x here, we will get this to one of these two equations, right. So, that is how we are reducing 4 coefficients, 2 square 4 to n minus 1 square, 2 minus 1 is only 1. But again these two, they seem to be different, but they are not. Let us see how. Because we can write V1 bar dou C1 by dou x plus V2 bar dou C2 by dou x equal to 0, which means dou C2 by dou x is equal to minus V1 bar over V2 bar dou C1 by dou x. So, if we substitute in the equation for J2 tilde, we should get negative negative positive D22 tilde 1 times V1 bar over V2 bar times dou C1 by dou x. Let us call this equation 1. But we know, because we are using volume fixed frame, V1 bar J1 tilde plus V2 bar J2 tilde equal to 0, which tells me J2 tilde equal to minus V1 bar over V2 bar J1 tilde, and if we substitute for J1 tilde from here, we get V1 bar over V2 bar times D11 tilde 2 dou C1 by dou x. Let us call this equation 2. So, if we compare the right hand sides of 1 and 2, it tells me D22 tilde 1 should be equal to D11 tilde 2. So, both the equation coefficients should be same. So, in binary, in effect we have only one coefficient, and we can express both the fluxes using one coefficient. J1 tilde, we call it as D tilde minus D tilde dou C1 by dou x, and J2 tilde is equal to minus D tilde dou C2 by dou x. So, the binary interdiffusion simplifies to just knowing one interdiffusion coefficients. Clear? So, varying partial molar volumes is a complicated case. Okay. So, typically during the experimental measurements, it is commonly assumed that the molar volumes remain constant. If the molar volume is constant, what does it imply? It implies that all the partial molar volumes are also constant and the same. Okay. You can show this. So, this implies that all that means V1 bar equal to V2 bar equal to V3 bar for an n component system. This makes the life simpler, because it not only simplifies the constraint. For example, sigma Vi bar Ji tilde should be 0, and since all Vi bars are same, this just implies to that sigma J tilde equal to 0. It also means that uv, the velocity of volume fixed frame, is 0, because there is no change in volume, there is no net flow of volume even in lab fixed frame. And since because of that, J tilde is equal to J0. So, the volume fixed frame coincides with the lab fixed frame. J0 refers to the fluxes determined in lab fixed frame. Okay. And that is why for experimental analysis most of the time molar volumes are assumed constant. In fact, we will show it later, even when the partial molar volumes are constant, but changing, which means V1 bar not equal to V2 bar, not equal to V3 bar, but Vi bar themselves are constant with composition, that even in that case uv equal to 0, and the lab fixed frame coincides with volume fixed frame. Clear? So, we will stop here for today.